Welcome back. In this lecture, we're going to study the concept of an inference rule, which is central to the notion of an argument. So first, let's review the idea of a valid argument by giving a couple definitions. Remember that an argument is a sequence of one or more propositions, the last one of which is called the conclusion, and all the other ones are called the premises. So in other words, an argument is basically a series of premise number 1, premise number 2, etc., premise number n. Each one of these is a proposition, and the argument ends with a conclusion, which is another proposition. So taken together, these constitute an argument. So let's look at a simple example that will look familiar to you. Let's say statement number 1 or proposition number 1 is, if the program crashes, then it does not produce a result. I think we all agree that this is a proposition. Let's look at another proposition, S2. The program produces a result. And then a third proposition, S3. The program does not crash. Now, since these are three propositions, taken together, S1, S2, and S3 constitute a sequence of propositions and therefore an argument. By our definition, S1 and S2 are the premises and S3 is the conclusion, because the assumption in an argument is that the last proposition, the conclusion, follows from the premises. That's why I added the word therefore in parentheses between S2 and S3. Now remember, when we talked about arguments before, the first step was to formalize the argument. That is, to translate each one of the propositions in the argument into logic. So I'm going to go fast on this one since we translated a similar argument before. S1 is a conditional. C implies not P, where C stands for the proposition, the program crashes, and P stands for the proposition, the program produces a result. The second proposition, S2, translates to the atomic proposition P, and the sentence S3 translates to the compound proposition not C. And to indicate that those three sentences go together and form an argument where the conclusion is a consequence of the premises, we usually use this symbol to indicate therefore, and we sometimes put a line between the premises and the conclusion. Notice that the words premises and conclusion have a loaded meaning. It implies that one should be able to infer the conclusion from the premises. But that is not part of the definition of an argument. So we need a new definition to define that concept. So we say that an argument is valid if and only if its conclusion logically follows from its premises. In other words, an argument is valid is from the conjunction of its premises we should be able to infer the conclusion. Another way to say it is that the conclusion C logically follows from the conjunction of the premises. Or in other words, whenever P1 and P2 and ... and Pn is true, then the conclusions should be true. That's the definition of a valid argument. So going back to our example here, this argument is valid if whenever S1 and S2 are true, then S3 is also true. In other words, S3 is a logical consequence of S1 and S2, the conjunction of its premises. Now we can translate that into logical consequence of propositional logic, since we did the conversion. And so the argument is valid if the proposition not C, in this case, is a logical consequence of the proposition C implies not P and P. Now to establish the validity of the argument is the second step, which we're now going to focus on. And to do this, we will need the concept of a rule of inference. So let's define rules of inference. A rule of inference is a template for a valid argument. So the first thing is that a rule of inference is an argument. Therefore, it must have one or more premises and it must have one conclusion. But it's a special kind of argument that we call a template. So let's illustrate this definition with an example. Probably the most famous rule of inference is called the Modus ponens, sometimes called the law of detachment. It states that if the premise P implies Q is true, and the other premise P is also true, then according to this rule of inference, you can infer that Q is true. So that's the rule of inference called Modus ponens. So the first question is, how are we going to prove that this is a valid argument, a valid rule of inference? And second, why do we say it's a template, not just a basic argument? Now let's answer question 1. How do we prove that modus ponens is a valid inference rule? That is, its conclusion Q logically follows from its two premises. Well, since this inference rule belongs to propositional logic, we can simply go back to our truth table algorithm. In other words, we're going to build a truth table for these three propositions, the two premises and the conclusion. And then we're going to check that whenever the two premises are true, the conclusion must also be true. So let's do it. Since the three propositions only use two propositional variables, the truth table will have 4 rows. And the next column will be for the first premise, P implies Q, which we can fill in now since we know this conditional truth table by definition, by heart. Then we're going to add a 4th column for the second premise, and then a last and 5th column for the conclusion, P or Q. Now notice we don't really have to add the last 2 columns here for P and Q, since these are already present in the truth table on the left. The reason I did it anyway is to emphasize the fact that to prove the validity of a rule of inference, we should have a column for its first premise, then a column for its second premise, and a column for each one of its premises, and then a column for its conclusion. And to prove the validity of the inference rule simply involves checking that whenever its premises are all true, in this case, it only happens on the last row, then its conclusion must also be true. And this proves the validity of modus ponens. So because we proved that the rule of inference is valid, what it means is that every time we know that this proposition is true, and we also know that this proposition is true, we can always infer that this proposition must also be true. And that's how we use a rule of inference. But there's a little bit more to it. What do we mean by a rule of inference is a template? Well, what we mean is that this rule of inference is really a general form of an argument, which says that every time you have an implication that is known to be true, and every time we know the premise of the conditional is true, then we can infer the conclusion of the conditional. In other words, this is just a rule, but it does not only apply to the specific propositions, P implies Q and P. It applies to any conditional and any argument of this form where you have a conditional that you know to be true and its premise. In other words, P and Q in this inference rule can be replaced by any arbitrarily complex proposition. So let me give you an example to illustrate this idea of a template. Let's say we know that the following proposition is true, namely P exclusive or Q implies not R. And we also happen to know that P exclusive or Q is true. And now we can recognize in these two propositions the premises for modus ponens. In other words, if you replace the P in modus ponens with this compound proposition, and you replace the Q in modus ponens with this proposition, well, you notice that the second proposition is nothing but P, and therefore these two propositions match the template of the premises of modus ponens, and therefore the modus ponens rule allows you to infer that the conclusion of the conditional, in this case not R, must also be true. So the power of modus ponens, or any rule of inference, is not that it allows you to infer a single proposition once you know that two specific propositions are true. Instead, it allows you to infer an infinite number of propositions, because P and Q in this template can be replaced by any proposition of propositional logic. So please make sure to remember the name and the template for modus ponens, because again, that's one of the most important rules of inference. But there are others. So let's look at the second one. It's very similar, and the name is close. It's called the modus tollens. It starts with the same first premise, P implies Q. But this time, instead of assuming you know P, let's say you know that the negation of the conclusion is true, not Q. Then what can you infer? Well, the template says you can infer not P. So in other words, if you know that P implies Q is true, and you know that not Q is true, you can always infer not P, whatever P and Q happen to be. They could be any arbitrarily complex proposition. Again, this is a template. Now I'll let you prove the validity of modus tollens using the truth table algorithm. I'm not going to do it on the slide. I'll trust you to do that. Another way to convince yourself that this rule of inference is valid is that remember how P implies Q is logically equivalent to its contrapositive, which is not Q implies not P. Well, if not Q implies not P is true, and not Q is true, then by modus ponens, using the previous template, we can definitely infer not P. So that's an intuitive argument for the modus tollens, but make sure to be at the truth table for it. So you must also remember the modus tollens. And while we're at it, let's add a third rule of inference. This one is called hypothetical syllogism. And like the first two, it starts with the same premise, P implies Q. But in this case, the second premise is another conditional, Q implies R. And what the rule of inference called hypothetical syllogism allows you to infer from P implies Q and Q implies R is simply that P implies R, which is a form of transitivity of the conditionals. Again, I will let you prove the validity of this inference rule, which is a nice exercise because in this case, since we are considering 3 propositional variables, the truth table will have 8 rows, so it's a nice exercise for you to review and practice truth tables. And hopefully you also understand intuitively why this rule of inference is true. If P implies Q and Q implies R, that means every time P is true, Q must be true. And if every time Q must be true, R must be true, then from P you can imply R. And that's called the hypothetical syllogism. So you will be responsible for knowing these 3 inference rules as well as the next one, which is called the disjunctive syllogism. As the name indicates, this one is a little bit different. Its first premise is a disjunction, namely P or Q. And let's assume you also know that not P is true. Then this inference rule says that you are able to infer a new piece of information, namely Q. Now intuitively, it makes sense that if either P or Q or both are true, but you know that P is false, then it must be the case that Q is true. I will let you prove the validity of this inference rule using truth tables. But this concludes our first segment on the introduction to rules of inference.